My name is Matthew Williams, and today I'll be presenting a frequent pattern analysis of the National Bridge Inventory that I did. The objective of this study was to identify common traits among structurally deficient bridges through the use of a pattern analysis tool. And I did that of the National Bridge Inventory, which is maintained by the Federal Highway Administration. And specifically for this analysis, I used the 2022 inventory. It includes just under 735,000 bridges with 123 different attributes to describe them. It covers all 50 states, Washington, D.C., and then a few U.S. territories. It's a freely available data set that you can find at the link at the bottom of the slide there. To go with this data set is the recording and coding guide. And what that does is it defines each of the attributes. It defines any units of measurement that are needed to understand those attributes. Some of the attributes are recorded as codes, and so the recording and coding guide will define what those codes mean so you can translate each record into usable information about that bridge. So out of all those attributes listed there, these are the ones that are going to be of the most interest here, starting with the age of the bridge, and then where the bridge is located, the type of structure, the type of deck on top, the material used to build the bridge, and then the bridge condition. And the bridge condition is provided to us on a scale from 9 going down to 0. And that is done for the deck, superstructure, and substructure. And then the lowest of those three ratings, they also report in the lowest rating attribute, which is a handy way to just say, what's the minimum rating of this bridge? So before we get too deep into this, we'll talk about the components of a bridge. So to start off with is the deck, and that's up top. That's what you drive on when you're crossing a bridge. The deck is supported by the superstructure. So in this picture here, the bridge in the foreground is a steel girder superstructure. The next bridge behind that one with the white SUV on top is a concrete girder superstructure. The superstructure is then supported by the substructure, and those are the vertical piers and the pier caps, and it also includes a footing, which is down below the soil and continues on down into the ground. And this is a pretty common type of bridge, as we'll see in a minute here, but I just wanted to give you a little bit of the lingo here. So as far as the methodology goes, the analysis was performed in Python, running on a Google Colab notebook. The libraries included PySpark, Pandas, NumPy, and Matplotlib. Part of the PySpark library is fpgrowth, which is a parallel algorithm that generates frequent item sets and association rules. And we'll get into more about what those rules are in just a second here. To look at the data set as a whole before we subdivide it into between all the bridges and the deficient bridges, we'll look at the breakdown of the bridge types here. So you can see that the most common type of bridge in the data set are girder bridges, and that's the photo that we were looking at just a second ago. That's a girder bridge, and that includes both concrete and steel, and there's just over 300,000 of them in the data set. The second most common type is a culvert, and we'll get into that in just a minute, and we're actually going to be dropping that from this data set, and we'll talk about why. Your fancier bridge types like arches, cable stayed, and suspension bridges make up a pretty small percentage of the total inventory. As you can see, the blue lines trailing off as we get down into the more rare types of bridges. So looking at the age of the bridges, here's a distribution of that. There's a lot of bridges between 0 and 50 years old, but then we do have a spike of bridges in the age range of 50 and a little bit above there. It looks like halfway between 50 and 75 years old. And that's important to know because for a long time, the design life that bridge owners sought and engineers aimed for was 50 years. So there's a number of bridges in the inventory that are getting up there in age. This isn't to say that they would need to be replaced immediately just based on their age, but um, it is interesting to note that there are that many bridges that are over 50 years old. Some bridges, especially the more complex bridge types, are designed to much higher design lives. So it's hard to get a full picture of how bridges are aging without their design life, and we'll get into that more in a minute, but this is an interesting breakdown of how old the bridges in the data set are. And then if we talk about the number of spans, so a span is the superstructure that goes from one pier to the next pier. That's one span. So most of the bridges in the data set lie between 1 and 4 spans. That's a typical size. And then beyond that, the numbers kind of trail off. So now we'll talk about the bridge ratings. And so on the right, you can see our scale. It starts at 9, with the bridge being in excellent condition, going all the way down to 0, which is a bridge that has failed structurally. And so if we look at the distribution of the overall bridge ratings, there's very few that are in excellent condition compared to the whole data set. There's a lot that are in good condition, and then things kind of trail off. And luckily, we don't see a lot in the critical, imminent failure, or failed ratings there. But in order to process this and get association rules from FP growth, I found it necessary to group these ratings. And so in my analysis, I grouped ratings 9 and 8 and considered those to be in excellent condition. Conditions 7 through 5 were grouped into a good group, and then anything below 5 is considered to be in poor condition. And it's this last group that we'll deem the deficient bridges, and it's those that we're going to be studying with the FP growth analysis. So to get the data ready for the analysis, the first thing I did was drop culverts from the data set. And so we'll talk about why. On the bottom right-hand side, you can see a culvert. This is actually a fairly large culvert, actually. So most culverts are not quite, don't have spans quite that long. They're typically a buried precast box that goes under the soil, and it's just a different structure type from what we think of when we think of bridges, with piers and girders and spans, maybe even cable stays or arches. This is a buried structure, and so we're going to kind of pull this out of the data set and look at just deficient bridges. So the bridge records that were missing the attributes that we cared about were dropped. I talked about grouping of the 9 condition levels. I also grouped bridges based on their location, and so there's a map on the right-hand side there, and you can see the 6 different regions of the U.S. That were considered here. And then you saw the plot with the number of spans, so bridges were also grouped by the number of spans. And the reason to do this is that FP growth is looking for frequent patterns. And so if we have, let's say, all 50 states in there, there may not be patterns there may not be enough patterns within a single state to show up in the resulting rules because the bridges have been, in a way, overclassified in their location. So I simplified their location, the conditions, and then the span numbers in order to get better results out of the pattern analysis. And so this was an iterative process, but this is what I settled on in the end. All of the attributes had to be converted to a unique item. And so if the number of spans was 3 and the age of the bridge was also 3, FP growth would throw an error because the two items have the same name and it doesn't know what to do with them. So all of the values had to be unique. And then I carved out only the deficient bridges into a new data frame or data set in order to put through the FP growth algorithm. When I put the entire data set through the algorithm, because the overwhelming majority of the bridges are not in poor condition, the rules did not pertain to deficient bridges. So I found it necessary to compartmentalize that and analyze those separately. But we do some comparisons back to the full data set, and we'll get to that here momentarily. So here's some example association rules, and we'll talk about how to read these. So rule number 1 here, the antecedent is 1 to 2 spans, and then the consequent is 76 to 100 years old. And so if we dive right into confidence level, it'll help sort this out. So the confidence level is 31%. So what this rule is saying is that of all the 1 to 2 span bridges, 31% of them are 76 to 100 years old. In the second rule, similar, bridges that have a good substructure and a cast-in-place concrete deck, 63% of those bridges have a substructure that is in poor condition. So that's what the confidence is telling us. We're not going to get into lift right now, but support is another interesting one. So that is telling us that 19% of all deficient bridges are 1 to 2 span bridges that are 76 to 100 years old. So for rule number 1. Rule number 2 is the support value is telling us that 16% of all deficient bridges are bridges with a good superstructure, cast-in-place deck, and have a poor condition substructure. So that's kind of how we go through that, and then we'll get into some rules that really help us learn something about this. So when I looked through the resulting association rules from FP growth, there were certain items that came up frequently within those rules. And so a lot of the rules pertain to cast-in-place concrete decks, girder bridges, bridges in the Midwest, steel girder bridges, and then, of course, bridges with decks, superstructures, or substructures that were in poor condition. It should be noted, though, that one of those has to be true in order for the bridge to be in the deficient bridge data set. So we'll talk about that here in a second. So the rules that came out of the FP growth analysis that were seemed to be the most meaningful were these. And I whittled this down from almost 400 rules down to these 6 that we're going to talk about here. So rules number 1 and 2 are interesting. So rule number 1 tells us that 73% of bridges with a deck that's in good condition has a substructure that's in poor condition. And rule number 2, 77% of bridges with a superstructure in good condition have a substructure that's in poor condition. So that's 2 cases here where these rules are pointing to the substructure as the problem. Next, rule number 3 just tells us that 44% of cast-in-place concrete decks are in poor condition within the deficient bridges. And so that's what you have to remember here, is that these rules were derived from the data set that included only deficient bridges. So that's kind of part of the antecedent that's not showing up in the rules. You have to remember the pool of bridges that we're pulling from here. And so rule number 4 pertains to steel girders. And then rule number 5 is an example of a rule that had a regionality item to it. So Midwest bridges with a good superstructure that are 1 to 2 spans long, 79% of those have poor substructure. But you have to think about, how many bridges are in that particular region versus how many bridges are in the other regions, and then ask, is it proportional? Is the Midwest section just bigger? So there's more digging to be done. And then I included rule number 6 because it can be a little misleading. So you'll notice that the confidence level here is 100%, and so that's a bit high, obviously. But so the reason it's at 100% is because of the box that I've drawn here. So the bridge has a good superstructure and a good deck, but a poor substructure. So that's kind of a requirement of being within this data set, is that one of those 3 has to be in poor condition. So that the 100% there can be a little tricky to interpret. You have to keep in mind why these bridges are in this data set. So then there are a few rules that pertain to the age of the bridge, and I pulled these apart because if you look at rules 1 through 3, all pertaining to bridges between 51 and 75 years old, about 60% of those bridges across the board, good deck, good superstructure, but poor substructure. And 60% of bridges 76 to 100 years old also had poor substructures. So again, this is pointing in a direction towards substructures being an issue. When you're looking at these association rules, it's important to keep in mind what you're not seeing. And so what I did not see as common items within the rules were concrete girder bridges. Those seem to be absent from this data set. Bridges from other regions. The Midwest was the only region that showed up, at least using the minimum support and confidence ratios that I specified. But then also complex bridge types were missing from this data set. But as I mentioned earlier, complex bridge types are fairly rare within the inventory, and so this is kind of expected. But all of this leads to wondering whether or not any particular item in the deficient bridge association rules is out of proportion with their prevalence in the total inventory. And so we'll look at that next. So starting with steel girders, within the total bridge inventory, at least the bridges that had all the attributes we needed to look at, which was 413,000 bridges, so 23% are steel girder bridges. But within the deficient bridge subset, 43% of them are steel girder bridges. So you can see here that the steel girder bridge is making up a higher percentage of deficient bridges than it makes up of the total number of bridges. So that points to steel structures being perhaps susceptible to degradation. Another one we hadn't talked much about is wooden decks. There's only 7% in the total. That's to be expected. Wooden decks are primarily used only on historical bridges and pedestrian bridges. So they make up 7% of the total number of bridges, but 23% of deficient bridges. So again, this is one that's kind of overrepresented in the deficient bridge group. The cast-in-place concrete decks actually seem to be doing pretty well. They make up 71% of the total bridge population, but only 55% of deficient bridges. So it seems like the concrete decks are holding up pretty well. And then the concrete girder bridges and the bridges in the Midwest, those percentages stayed roughly the same. So concrete bridges or concrete girders they also seem to be holding up well because they make up the same proportion of deficient bridges as they do total number of bridges. So they're, you might say, behaving as expected. And then lastly, we're looking at the how often each of the three structural systems is in poor condition. And you can see here that the substructure is over 50%. It's the highest of the three within the deficient bridges. So that's another pointer towards substructures being a potential issue with regards to longevity. So to wrap things up here, some of the findings and recommendations that come from the study, the number of bridges over 50 years old does speak to the need for careful monitoring because they could potentially be past their design life. Steel bridges and poor substructures are disproportionately represented in a deficient bridge data set, so that deserves some attention. Number three, it would be really interesting to have the intended design life as part of this data set, because then you could compare it to its actual design life and get a feel for how many bridges are being used beyond what they were designed for. I think that would be a very useful statistic to have. And then finally, I would recommend studying the deficient steel bridges and deficient or bridges with deficient substructures to identify potential ways to improve their condition, slow down the way that they're degrading, or even look for ways that the design of these components could be improved so that the bridge degrades more or less uniformly and it's not one particular system that's dragging down the condition of the entire bridge.